So let's proceed further. So we have seen, so in order to generalize this, whatever we have discussed, so now we consider that always we know x is a random variable, and we say that a is an event which we define now is x is in between some number a to b, and where a b are two constant, a b are constant and a less than b. Then what we could say? We could say that f of x given a, where a is a x is less than a and b. So this event a, let's write it as the event a. What is this? We can write it. We write it as the event a less than x less than equals to b, and in brackets small x, all of us know. So this will be nothing but f of probability of, we have seen earlier, this is the probability of x less than equals to x and the probability of x less than equals to b divided by the probability of a less than x less than equals to b. Okay, so now we need to evaluate this probability. Now let's try to think. Suppose we have this kind of number line where we have a here, where we have b here, and this is x, and small x can go less than b, in between a to b, and more than b as well. So if we see here this region, that means our small x is less than equals to a, then the event x, then the events, two events I am calling capital X less than equals to small x, and another event that a less than x less than equals to b. These two events are mutually exclusive, are mutually exclusive. Let's see Satipriya is there or not. She is always late, so just give me one call.
Yes, sir. I'm here.
Oh, you are here. Okay, fine. You joined. Okay.
Yes, sir.
So these two are mutually exclusive. Why? Because we are considering the number in this region, and we have the event which is in this region. So these two are mutually exclusive. There is no intersection. So the conditional CDF for these two will be equals to 0. Now let's consider another region, this region, okay, another region, this region. So this region is, now let me write, for x greater than b, okay, the event x greater than b, and the event where a is x is in between a to b. You can note it that I am going greater than a and less than equals to b. That is why I am going here greater than b and here less than equals to a. Okay, so this is very simple to note. So these two events, x is greater than b and the event a, x is in between a and b. Okay, so these two events, so these two events, that means here it obeys. So the intersection of these two events, basically these events, the events this is a subset, of x less than x. Okay, so hence we can write that so for x greater than b, the event when it is here, the event where x is in between a to b is a subset of this. Okay, obviously, because we are considering x here and it is full we are considering, and then this event is a subset of this full line. Okay, so it is a subset of this. Hence, we can write the probability of x less than equals to small x and a to b to less than equals to small b will be equals to probability of a x less than b. Is it okay? Because we are considering the probability less than this, and the intersection is this. So it is a less than x. Okay. So the conditional CDF will be equals to 1. Now, when it is in these two region we consider, when it is in this region, what does it mean? So when next we consider when a less than x less than b, then what happened? Then happened that probability of, I'm jumping one step, probability of x less than equals to small x and a less than x less than equals to b will be equals to the probability of a x less than equals to x. Now if we write, so if we write this earlier one, whatever we have considered, this one, now how we can write, let's see. No, I am writing now directly, so you may be frustrated with so many steps. Let's write directly. So a less than x less than equals to b of x will be equals to, now tell me, if x is less than a, what this will be? This is, it is less than
0.
a, 0, yes, it is 0, yes, 0. So now if it is greater than b, what it will be?
1.
1. Fine. Now the next thing comes when it is less than equals to less than equals to b, and this is when x is a to b. Let's write the denominator first. This is fx of b minus fx of a. Everybody agrees? This one? This one, you note a to b, that means we took the fx of b full minus the fx of a. We took the full probability of this and then the cumulative probability of a. So if we subtract this, we will get the probability of this, right? Fx of b minus fx of a. Everybody agrees this denominator?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So now yes, it is obvious. Now if you see the numerator, which is the combination of x less than x and a to b, that means you have to do fx of x. So this could be anywhere. So fx of x minus fx of a, then only you will get it. Okay, so it is, we can write fx of x minus fx of a. Everybody agrees?
Yes, sir.
Okay.
Yes, sir.
Anybody has any doubt? I can explain it. Okay, no doubt. Fine. So this is a kind of regular extension of whatever we discussed. The same thing yesterday we discussed. It is kind of extension a to b. Earlier we discussed less than a, but it could be in between the two number. So this is a kind of extension, obvious extension of the yesterday class, whatever we discussed. Now let's see how we can define a conditional PDF. So conditional PDF. So actually here this PDF, sometimes I'll write capital P, capital D, capital F. So I'm trying to follow this thing, but generally I write in other place small p, small d, small f. So it's kind of getting interchange. Okay, so don't mind. Now you see the conditional probability density function of a random variable x. So the x is a random variable and a is an event which already occurred. That means we can write PDF of x given a of small x will be equals to limit epsilon tends to 0, probability of, same way I am writing, probability of small x less than equals to capital X less than x plus epsilon. So one side I will give equals to, less than equals to, another side not, because in the next interval that will be equals to, it is obvious, given a divided by epsilon. Okay, everybody agrees? Same thing. So only we are writing the joint. If there is no probability of this by not given a, it is joint, so it is given a. So it is quite obvious. So now the properties, all the properties of PDF is obeyed by the conditional PDF. So let's write it. It is very obvious. X given a, small x is equal to 0. Second is f of x given a, small x will be equals to d of fx given a by dx. Now 3 is f of x given a, small x will be equals to minus infinity to x f of x given a, small x, or we can take y, then x is come, y dy. We know minus infinity to plus infinity, f of x given a, small x dx will be equals to 1. Now we see a to b, f of x given a, small x dx will be equals to probability of a x less than equals to b given a. Okay, a to b, that means probability of a to b given a. So these are obvious. Now okay, oh, now the page is finished. Okay, I need to generate another blank PDF, so let me do it. I need something, presentation, just little bit wait. A blank PDF is required, so it is just 1 minute, little bit. Microsoft PowerPoint. Okay, close this one, copy, paste. Just 1 minute. Where is the keyboard? Okay, let's save it. Print it. Okay, now hold on. Okay, fine. Now you can see, right, this blank thing.
Yes, sir.
Makes it to size 13 1. Okay, so now we have seen that all the condition or all the properties of a PDF that is also obeyed by the conditional PDF. That is obvious, we know it. Now suppose I will give some example what is the meaning of conditional PDF and how it changes. Suppose I am drawing a PDF which is unconditional. That means x versus fx of small x, and let's say it looks like something like this arbitrarily. Okay, something like this, or something like this. Okay, so it is unconditional PDF. Now if I identify 2 points, one is say A and another is say B, and I want to draw a conditional PDF. So this is unconditional, you can see. Now if I want to draw fxa of small x, how it will look like. Okay, so how it will look like. So you can see it will look like the first thing you can see that if it is a conditional PDF where is A is an event, A is an event where small x, capital X will be in between A to B. It means, let's say this is A and this is say B. So there will be nothing apart from A to B, because we already conditioned that the PDF given the event is in between A to B. So this region will be definitely 0. Okay, this region will be definitely 0. And then what about this region? It is like this. But you see the same thing you cannot draw, because here the area over the curve is unity, and then here it becomes 0, but the area over the curve of conditional density is also should be unity. So this will be little bit up. Okay, so if we draw it, it may look like more up, maybe something like more up and something like this. Okay, or maybe symmetrical it should not be, maybe something like this. Okay, so now you see that the area to remain unity, it will be little bit up. but there will be nothing in between A to B. So we can calculate it and we can exactly do it. This is kind of sketch, or I am trying to giving you some idea. People might be sometimes think that if a condition A, where A is in between A to B, the A to B will remain, other will be wiped out, and the curve will be same. That is not, because curve cannot be same. Then the area under this A to B will not be unity. Curve will definitely will rise up, but exact shape you will know, and after you calculate this mathematically, this conditional density. Okay, is it to all of you this discussion? I'm trying to give little bit insight or physical description. Okay, please tell me any doubt up to this point.
No, sir.
Okay,
No, sir.
everything is fine, right? So what I am saying, it is, yeah, it is making some sense. Okay, then let's do one example. So let's a random variable fx, probability PDF of random variable fx of x will be, let's say, whatever this book is given, 1 by 3 e to the power minus x by 3 into ux. Okay, so now I want to say that what will be the conditional probability, conditional PDF, when a, the event A is considered as, the event A is considered as x greater than 2. Okay, so here it is ux, you can see that means it is 0 to plus infinity, but we consider an event which is x greater than 2. So that means our condition is 2 to infinity. Now then, what will be fx of given x greater than 2 of small x? Can you calculate it quickly? Very quickly.
Sir, is it 1 by
Yes,
3
tell me.
into e to the power 2 minus x
Hmm.
divided by 3?
Yes, and then u.
Yes, sir, u to the power x, where x, like x is between 2 to infinity.
No, no, this is fine. And then it will start from where? It will start from where? Range. Range
Uh,
of x.
x, sir, from 2 to infinity.
Yeah, so you should write ux minus 2, right? Step function. Did you get this? Joyce, you are speaking, right?
Yes, sir. Yes, sir. Yes, sir. I got this.
No, who said this answer? This is correct. Joyce or Joyce only said, na?
Yes, sir.
This one. So ux minus 2 you should write. Then only you will get. Okay, let's do it. So now let's solution. So suppose I want f of x where given uh, x is in between, say x is in between a to b of small x, then because the a I am assuming a is an event which is this one, okay. So x given a, that means we can easily write it, this will be equals to, so this will be equals to, so in between a to b, let's see, in between a to b there it exists, but otherwise will be 0, that much is sure, otherwise it is 0. Now in between a to b what it will be, so in between a to b it will be like the earlier we have seen, it will be in between a to b, it will be fx of small x divided by probability of a less than equals to x less than b. Do you agree, everybody? This one, everybody agrees?
Yes, sir.
Or okay, or who is not comfortable with this expression? Asna, you said yes, right?
No, sir. No. Sir, can you please explain this?
Then who said yes? I'm not getting face now. That is, huh?
Sir, I said Sastria.
Kirti, as a Shreya. So can you explain it for others?
Sir, here the
How it is coming? Hmm.
sir here it is said that we have to find the probability of f of x at x divided by the,
Hmm.
if we give the range in between, we are finding the condition, that is a
Hmm.
that is x which is greater than equal to a less than b, then we will be getting the
Hmm.
PDF that you said earlier, like
Hmm.
we have to divide it, like the range you draw and set the limits a and b, and there you said that we have to divide it
Therefore,
by
what
the,
do you say? Fine.
so
Therefore,
that one.
is it fine, this expression? Hmm.
Yes, sir.
Yes, sir.
Hmm.
So
Fine.
is it
So can you,
less or
yes.
equal to,
Yes.
or is it less than?
Which one? This one. Yeah, it will be less than definitely.
Thing?
Just 1 minute. One bound it will be. Now, can you explain it?
Yes, sir.
Yeah, this one. Could you explain physically what, how it may intuitively we can
Uh,
see that this is correct, right?
yes, sir. Sir, if we see the property of PDF, that is, if we have to calculate that from in between 2 points, then we simply take the probability in that interval, or we integrate between that interval. So since the properties remain same for the conditional PDFs as well, we can use that, sir, that given this condition, if this is the condition, we can use that same thing here.
Yeah, the same thing like earlier we discussed. So that is by the probability of that. Earlier CDF we discussed, not the same thing. Now if we apply this one for our problem, then how it will get? So what we will get? That is the question. So here the event is x greater than 2. So what will be the probability of x greater than 2? Tell me what it will be. It will be integration 2 to infinity 1 by 3 e to the power minus x by 3. So what it will, quickly can you tell me quickly?
e power minus 2 by 3.
Yes, e to the power minus or plus?
plus minus, sir.
Plus 2 by 3, right? As a minus. Okay. So then what will be our f of this? So then f of x given a, sorry, this one, x given x greater than 2, small x, will be f of x divided by e to the power minus 2 by 3. That you mean to say, right? So then this will be for this range. So this will be, what is fxx? It is 1 by 3 e to the power minus x by 3. So 1 by 3 e to the power minus x by 3 into e to the power 2 by 3, right? So what did we get? We get 1 by 3 e to the power 2 minus x, 2 minus x by 3, right? And we know that if it is greater than 2, that means below 2. If it is 2, this will be 0 before 2. After 2 only it will start. So we can write f of x given x greater than 2, small x, will be 1 by 3 e to the power minus 2 minus x by 3 into u of x minus 2. U of x minus 2 means from here step function will have unity, and we multiply unity with this before we multiply 0. So after 2 there is starting. So it will be 1 by 3 2 minus x by 3. Okay. So this is the conditional. So everybody agrees with this?
Yes, sir. Yes, sir.
Yes,
Yes.
sir.
Okay. Okay, fine. So now you see, there is a good property you can see. So fx of x greater than 2x will be equals to fx into x minus 2. You see, so fx is e to the power, sorry, fx is e to the power minus x by 3, and we multiply it with the x minus 2, and then you will get it. So anyway, so it's okay. So similarly, different kind of problem we can formulate. Now it is interesting to see. So this is for continuous. Now for discrete, how it will look like. So for continuous it is fine till this point. Then if anybody has any doubt, you can ask quickly. Okay. Now what will be the discrete? If your distribution is discrete, that means PMF. How we characterize the discrete distribution? It is a kind of probability mass function, not the probability density function. So assume. So this is also very important, because you will see when you do research on stochastic process in maths, maybe people are doing the continuous thing, and but in engineering, very few people, continuous thing is kind of rare. Always you have to go, even if you get the continuous PDF, you have to discretize it. The main reason is that you have to incorporate computer to calculate, or to calculate the algorithms. To implement the algorithms, you need to implement the computer. So the continuous domain evaluation is very rare. Mostly what we do, we get the Gaussian PDF or some other PDF, but we discretize it, and then it becomes a discrete PMF, probability mass function. And this discrete PMF, we keep on working with it, because computer needs a number and points and something. So it is very important to see that the distribution could be discrete. So discrete distribution, discrete, sometimes we call discrete PDF, and it is same as probability mass function. You will see in research literature people used to say discrete PDF. Probability mass function could be the more appropriate way to say, but people don't say it. So now if you see, then what will be the probability density function, or the discrete probability density function with some condition. Okay, so that is very important to know. So now if you see, if you consider a set of mutually exclusive, so let's say a1, a2, a3 dot are the mutually exclusive and exhaustive conditions. So we want to access the CDF. Still we are in continuous domain, but we have the mutually, there are many events A1, A2, A2, AN, which are the, so we say that f of x given an of small x, where n could be 1 2 3 4 dot dot capital N, so up to a capital N are mutually exclusive event. So you could write f of x an, so x where n is will go 1 2 3 to capital N. So then how we could write the fx? So how we could write fx? That is our question. Okay, so we know fx of x will be equals to probability of x less than equals to small x. Now could say this is given an into probability of an. So we are assuming the theorem of total probability. Total probability. We know that the total probability, we can write probability of this with this. So we can write it n equals to 1 to capital N f of x given an small x to probability of an. Okay, so this is of what we can write, and similarly we can write the PDF of x will be equals to n equals to 1 to capital N. Then we can write fx given an of x multiplied by probability of an. Okay, this is a very simple way to write. Now I was telling about the discrete PDF and all PMF. So we can write that discrete PDF with the help of Dirac function. I'll come to that later. Now with this there is another issue. So till now what I was discussing, that always I want to calculate the conditional CDF or conditional PDF, and there I see that how the probability is coming into that, and I always give example that what will be the conditional PDF of that, this, that, and what will be the conditional CDF you calculate. But now I want to say there is its reverse problem is also very important. What does it mean, the reverse problem? So we can think of looking the same thing in a reverse direction. What does it mean? It means suppose we observe a random variable and the observation takes place, say random variable takes a point small x, then what will be the probability of any event A given that observation, whether it will be same or it will be different. So what I'm trying to explain, so now I am trying to see the reverse problem. What does it mean, reverse problem? Suppose I observe a random variable which is capital X equals to small x, and then we have an event an. Okay, so if we observe this and then the probability of that event an given that observation x equals to small x will be will it be same as probability of an? Okay, so that is the question. Definitely it will not be same, definitely it is not be same, but we are trying to look that suppose we have an observation and we have formulated some event. So after the observation the probability of that event will be same or different, or how we can calculate the probability of that event after the observation. So this becomes very important because in engineering you will see that we frequently keep on observing with the help of some sensors or with the help of data. Those who are working stock market and all finance, particularly Joyce and Mridul, you will see that you have some observation that after price, what is the stock market price or something else. So you have the observation. Now those who will be working on the sensor data processing, they will see at some point of time we get this measurement. So if we observe it, then what will be the probability of some event given that we observe something? So basically it will not be same. So and what it will be, that is our now next question. So now if we see and if we see, we can write like this: probability of an given capital X equals to small x. This will be probability of x equals to small x given an into probability of an divided by probability of x equals to small x. So now here you see we are assuming it is a discrete function PMF. Otherwise probability of small x equal to capital X equal to small x will be 0. So it has no meaning. So we are considering that we have a discrete random variable, we have the probability for that, and we assume some event, and now we are saying that what will be the probability of that event will gradually generalize to its continuous variation. So now I am saying what will be the probability of that event is small x. So it is not a continuous. If it is continuous, then we need to take some other methods or we need to modify it. Now tell me this expression whether all of you agrees, or you may ask that how I am getting this expression. Anybody has anything to say, please? Can you explain how I get this expression? Anybody?
From Bayes theorem.
Yes, little bit louder.
Bayes theorem.
Little bit louder, please.
Bayes theorem. It's from Bayes theorem.
It is the theorem of total probability. Yeah, it is the theorem of total probability. So yeah, you can say this. It is a Bayes theorem because x equals to x given an opposite condition into an by below x equals to x. It's a Bayes theorem. Okay, so now if we agree with this, then we say that it is for continuous, this expression is not valid. Because why it is not valid? Because we know at the continuous, if your distribution is continuous or something, at some point, say what is the probability of getting this number when it is continuous? It is 0. Obviously it is 0. You will get some probability if you give the range. So p of x given this, it becomes 0. So for continuous random variable, PR of x equals to small x equals to 0. Hence this we cannot carry with it. So we need to do something. It is not very difficult. So to avoid such problem, we will define that. So if to avoid such problem, we define the event x equals to x small x. We don't say. We say the event is getting x in between x plus epsilon. Okay, this is a very general way to, and we say that epsilon tends to 0. So now let's see that. So So then what is our probability? I'm writing this expression again. So probability of an given x equals to x. Instead of that, I'm writing it probability of an given this capital X is in between. Sorry, wait, just okay. Now it is fine. So probability of an given x less than equals to x less than x plus epsilon. See, instead of x we make it x plus epsilon so that it is not 0. So then how it can we can look like, right? The same thing here we'll write. So probability of in between x plus epsilon given a. Oh, I should, okay, let's write again. Here it is not accommodated. So this could be written as probability of, this one will come first, small x less than capital X less than x plus epsilon given, no bracket shouldn't, given an, then probability of an, probability of n by probability of small x less than capital X less than x plus epsilon. Is it fine? Everybody agrees? So if epsilon is very small, we can write the probability of this. We can write this probability of x in between x plus epsilon as fx of small x into epsilon. If we assume epsilon is very small, so we can assume that fx is kind of straight line in that region and we multiply with the epsilon, so we get the area. Okay. So similarly, this also we could write as, if epsilon is very small, we can write as this is probability of small x greater than capital X greater than x plus epsilon will be equals to f of, so this we can write as, this is f of x given an x into epsilon. So this probability means it is a conditional of, as this is a condition, so it's a conditional PDF multiplied by epsilon, and this is unconditional PDF multiplied by epsilon. So eventually we could write this as conditional PDF multiplied by epsilon and then probability of an as it is. Here also we could write the unconditional PDF multiplied by epsilon, and then epsilon will cancel both the side, so ultimately we will get the conditional PDF into probability of an divided by unconditional PDF. Okay, so now you see we have started like this, an given this. So now if we assume that the epsilon tends to 0, so we could write this as the probability of an given x equals to small x will be equals to limit epsilon tends to 0. Same here, if we take the epsilon tends to 0, if epsilon tends to 0, so we could write just this, I should write first, just 1 minute. You should write limit epsilon tends to 0 probability of an given small x, capital X in between x plus epsilon will be equals to probability of an given x equals to small x will be equals to f of x given an of small x to probability of an and fx of small x. So do you agree with this? So probability of some event given we observe this value, this will be the conditional probability of fx given that event and the probability of that event and the unconditional PDF. Okay, this is a very important formula. Many times we use it in statistical inference. Okay, now tell me if you agree or if you follow the full procedure. This is quite simple still.
Yes, sir.
Okay, what other says?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay, fine.
Yes.
Okay, fine. Okay, now you see, so this is the case. Now you see there is some one extension which is also very useful and frequently it is used in statistical inference. That is, we have seen that fx of x will be equals to small n equals to 1 to capital N. Suppose we are assuming there are n number of events. So f of x given and which are mutually exclusive and fully collectively exhaustive, fx of small x probability of n. This one we have seen. So probability density will be sorry. So probability density will be the conditional probability multiplied by the probability of that and then sum of all. Okay. So if we replace this here, what do we get? Probability of an given capital X equals to small x will be equals to conditional probability of x and probability of an by summation of n equals to 1 to capital N f of x given an small x probability of an, right? So now you see, if you want to know the probability of an, there are a1, a2, all those given that this has, we have observation. So we need to know the conditional distribution of that an and multiplied by the probability divided by the sum of all this. So this is also kind of Bayesian inference, and this lower one, this is a very important formula. Lower one we generally call is a normalizing factor, and many times it is not required. We say this is proportional to this. Okay, and this is a normalizing factor. Okay, now tell me, up to this point, do you agree? This is a very important formula we derived. So shall we go for an example directly related to this formula? So this formula is fine, right, to all of you?
Yes, sir.
So
Yes, sir.
so we can go directly, say example. Example is, suppose I am taking the example from the same book. So we have a swimming competition, and swimmers are categorized into two groups, group A and group B. Okay, the this is group A is for fast swimmer and group B is for slow swimmers. Okay, so you know that in class also we used to do it, categorize, so that the everybody feel competitive. Otherwise, if you put somebody who is very fast with some very absurd. So we have two groups A and B, and now that probability density function f of x given A will be 4 pi 1 by square root of 4 pi e to the power minus x minus 40 square by 4, a Gaussian distribution definitely you see. And you see probability of x, PDF of x given that b is 1 by same root over 4 pi, but mean is different, e to the power minus x minus 45 square by 4. Standard deviation is also same, mean is different. As you see here, the 40 is the first one, so and 45 is more, that it is a slower one. And also we assume that 30% of the swimmer are in group A, 30% are in group A, so 70% are in group B, definitely. Now I am asking the question, suppose a person or child swims a race with a time of 42 seconds. So we have observed a person, we don't know about the group, we observe a person or a child swims with a time of 42 second. Okay, so then what is the probability, what is the probability that the child was in group B? Okay, so what is the probability that a child is in group B? Solution. So here see, we have the observation a child 42 second, but we want to know that what will be the probability of that child in group B. That means what we need to know, we need to know the probability of B given x equals to, we observe 42, what it will be, right? So can you calculate it? Now it's looking not very difficult, right? Quickly calculate and tell me. Is it fine, the problem statement? So there are two groups, group A and group B. We know the conditional density function PDF, f of x given A, which is Gaussian, also f of x given B. So 30%, and then you calculate, we observe a child swims 42 seconds, what will be the probability that the child is in group B? Do it. Are you
Sir,
doing?
I'm thinking around like 0.995, like 99.5% chances.
No. You calculate again.
Sir, around 0.4.
Yes, 0.4. Fine. So let this we can write. So it of x given b at x means here 42, here x is 40. In probability of divided by sum of this. So this sum of this one. So fx of fx given a at 42 multiplied by probability a of b 42 multiplied by probability of b. This will be equals to fx of b at 42. What it will be? Have to put 42 here. So 1 by root 2 4 pi to the power minus 42 minus 45 square by 4. How much that is coming? Around 1 by root 4 pi will be cancelled. That I'm coming later. So we can write 1 by root 4 pi f of x given this, that is e to the power minus 9 by 4. Is that so, Jafar? Into probability of b means 70%. That means 0.7.
Yes, sir. That will directly be cancelled at 1 by root.
Yes, that will cancel, but I am trying to write it. Yes, 1 by root 4 pi. If x given a 42, this will be e to the power minus 1. Then probability of a, which is 0.3 plus 1 by root 4 pi. If x 42 means again this one e to the power minus 9 by 4. The probability of b, that means 0.7. So 1 by 4 will cancel out. So we'll get 0.7 into e to the power minus 9 by 4 by 0.3 into e to the power minus 1 plus 0.7 into e to the power minus 9 by 4. Okay, so and it will come something 0.4 as you see. Okay, so so you see that probability of having that child in B is 0.4, provided you see that the 42 is the. So you see that, so because here 40 45, you can see that. Okay, so similarly we. So now if I ask that what is the probability of this child being in group A, probability of being group
0.6.
A, yes, x equals to 42. That will be 1 minus probability of being group B, x equals to 40. 1 minus 0.4 plus 0.6. Is that fine for everybody? If you want, you can just see it, and if any query you have, you can. Kirti, Ramsam, Ramsai, right?
Yes,
So is
sir.
it fine to
It's fine.
is people? Yeah, Ramsai.
Yes, sir.
Yeah. So now you see, this is a very good thing we discussed, that this reverse problem, because it always comes to our engineering application, and we see that gradually we for proceed and we find this formula, that probability of a n given x equal to x will be equals to fx of a n p n divided by the sum of this, if all the event constitute mutually independent and mutually uh, collectively exhaustive, and they are mutually exclusive. Union all, you will get the sample space S universal set. So in that case, we can write it like this. Okay. So tell me if it is fine, then we'll move forward.
Yes, sir.
Okay. So we have completed this main theme of the our probability, whatever we need. A few more cosmetic things and few more calculations we'll do. But at least for one dimension case, the main theme we have covered. So PDF, CDF, conditional PDF, conditional CDF, all those things are the main. And concept wise also I try to discuss whatever we learn the concept wise, so that you don't get misled the proper understanding you receive. Okay. So it was going on 1 point something, that 1 point something, just 1 minute. What was it? Let me see this. 1.2. Okay, 1.2. Now it will be 1.3. Okay. Now it will be 1.3. Page number I should keep here. Sorry, page number I did not keep. 1.3. So this one we discuss that the some operations of on a random variable. Okay. So this is very simple actually. I try to discuss as much insightful I can. So first thing is that expectation. So how we can define expectation? So expectation of a random variable capital X. How we can define? Uh, with a PDF, with a PDF fx of x is very simple. E of capital X will be equals to minus infinity to plus infinity small x f of x small x dx, right? So this is the definition of expectation. We call it in a different name. For example, all are same. Expectation is same as average, same as mean, same as first moment. Okay, when we see that it's kind of, when I select that means you collect all the numbers and then sum it and divide it by the numbers, that is average. That means expectation is also that all the numbers are not equally probable. That's what we need to multiply x, we need to do the integration. Again, I'm trying to give more examples because
You're not audible, sir.
Can you see it now?
No, sir.
Yes, sir.
Okay,
Visible to
just
me.
wait. Yes, it will come gradually. Okay, now all of you can see Asna.
No,
No,
sir,
sir,
not
not
yet.
visible.
Okay. I don't know whose network is weak. Let me do one
Yes,
thing.
still visible to me.
It's
Hmm.
visible to me
It's
also.
Let,
also visible to me, sir.
okay.
But it's visible now.
So who is not seeing?
Sir, I cannot see, sir. Ram, sir.
Okay. Okay. Then try me the last thing which I can uh, switch the network. It may not be this side problem. Still, let me switch the network.
Sir, now it is visible.
Okay, now it is coming. Okay. Okay, now it is visible to everybody. So it will come. So what I was discussing, this expectation and average, I thought that both are different because these are the different formula, how it can be same. But you see that suppose we have a discrete numbers, when you do average in class 4 or 5 or very primary stage, we sum all and divided by n. There we assume that all the numbers are equally probable. That is the case. That's why there is no weightage. Okay, all the numbers are equally weightage. So we sum all and divided by the total count. Now, if the number is not equally probable, which is the case when we define the probability mass function or probability density function, then how do you average? So then to do the average, you have to take the number multiplied by the probability and then take another number multiplied by the probability. You take another number multiplied the probability and then you will get it. The other way of thinking is, suppose we have two numbers, one 0 or 1 or something else, and both are not equally probable. If it is equally probable, what will be the average? 0 plus 1 divided by 2, 0.5. If it is not equally probable, suppose the probability of 0 is 0.7 and probability of 1 is 0.3, then how do you do the average? That means if you have 1,000 numbers of trial, you will get 700 0 and 301. So you add all 700 0, you add all 301, what you will get? You will get 700 0 means 0, 300 ones, that means 300, divided by the total number, which is 1000. So that's what you will get. Okay. So this is the case. So if you have the probability, that means if you have the probability, that means you probability numbers are not equally probable. If you do very large number of trials, that means some number will come more, some number will come less. And if you see that how many more numbers are coming, how many less numbers are coming, you add them all, divide by all the count, we will get average. That will be same as this expectation or whatever you say. So basically the expectation is same as average. The formula differs because all the numbers are not equally probable. So you need to weightage the number with the probability of occurrence of that number. Then you
Sir, can't hear you again.
So you're not audible.
Quickly do it. Tell me what it will be.
Is it 1?
What it will be?
1.
No, 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 no. Not 1. It will be. It will be B. Okay, let's do it. E of x 0 to infinity. Why 0 to infinity? Because ux is there. X into fx, that means x by b e to the power minus x by b dx will be equals to what it will be. X by b you can take y substitution, so 0 to infinity x will be by e to the power minus x by b means e to the power minus y, then dx will be equals to b dy, 1b is there, so b 0 to infinity y e to the power minus y dy, right? What will be y e to the power minus y? Zero to infinity. So it will be b.
So B.
Okay. So another example. So we have seen the Poisson distribution. So the Poisson distribution px of k will be equals to, we take lambda, right? Lambda to the power k by e to the power minus lambda by k factorial. K could be 0, 1, 2, this. Now tell me what will be the expectation of x? Can you do it? We are going very fast. It's good. So now which mode do you like? This online mode or offline mode? What do you say?
Sir, expectation is lambda.
Yes, expectation is lambda. All of you please do it. Which mode do you like? Offline mode or online mode?
Sir, online mode has more flexibility. Like we can choose any time.
Yeah, that is different. Suppose time is fixed. I don't know. So my opinion is, if PowerPoint presentation is going on, then offline PowerPoint and online PowerPoint both are equally junk. Okay.
And this is giving us like the feeling of like we are in the class, like the class is going offline, like this way of teaching.
Yeah.
So we are not getting bored anymore.
Yeah. So only thing is that in offline mode, kind of in class, we generally have more interaction. I can see everybody's copy. I can joke, crack some joke or something. Okay. And online thing is very compact. I cannot see anybody, just delivery as a capsule kind of thing. Okay. Okay, quickly do it, all of you. So, Asna, you have already done, na?
Yes, sir.
Okay. What about Satipriya? Have you done it?
Yes, sir. Doing.
Okay, quickly you do. What about Kirti?
Doing, sir.
Kirti, you are MTech or BTech?
MTech, sir.
MTech communication.
Yes, sir.
How did you choose this course? None of your friend took it.
Yes, sir. We were given 5 choices for as
Hmm.
electives. I
Hmm.
chose this.
Peculiar, right? You are odd man out.
Yes, sir.
Okay. So you see, this will be um, xk means k only, right? K is 0, 1, 2. Pxk, k. This one is k. You note it. So here it will be k. So it will be e to the power minus lambda summation k will be 1 to infinity lambda to the power k minus 1 factorial, and this will be lambda e to the power minus lambda k equals to 1 to infinity lambda to the power k minus 1. All lambda I am taking out, k minus 1 factorial. Just some mathematical manipulation, nothing else. Equals to lambda to the power minus lambda m equals to 0 to infinity lambda to the power m by factorial m will be equals to will be equals to lambda to the power minus lambda to the power lambda equals to lambda. So mean is lambda. Okay. So mu x is to lambda. Okay. So now, if I say that, so I coming why we say that it is a first order moment. But apart from that expectation, you understand, average same, understand, mean you stay. First order moment we did not discuss till now. Quickly I am coming, very quickly. So now 1 point, what is that? 1.3. Okay, let's see 1.3.1. No, 1.3.2. 1.3.2. So it is suppose a expectation of a function. Expectation of a function. So the expectation of a function, so expectation of a function gx for the random variable x with PDF f of x small x is expectation of a function g of x will be equals to minus infinity to plus infinity g of x fx of x dx, right? Same. Mean was the first order, then x fx dx, gx is the same. So now for discrete random variable, e of gx will be equals to summation over k g of xk into probability of x xk, right? Okay. So now few results. If I ask what will be e of a is a constant, ax plus b. How we can write? A of ex plus b. How we got it? E of b constant is b. E of ax, that means a is constant, will go out, ax plus b, right? Now for similar thing, suppose a function gx is the sum of g1x plus g2x plus dot 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 plus gnx. So we can write e of summation over k is 1 to n gk of x will be equals to k equals to 1 to n. It will go inside e of gk of x. Okay, very simple. Proof is not required, it is obvious. Now we have seen the mean. Now we have the higher order moments. We'll discuss it. Okay. Tell me, today class, you have any problem, right? You don't have any problem of understanding, right? And the pace and everything is fine.
Yes, sir.
Yes,
Yes, sir.
sir.
Okay. Any
Yes, sir.
comments or anything? Any modification I need to do? Joyce and Mridul.
No, sir, it's fine.
Okay.
No, sir, it's completely good, sir.
Okay. So now let's go for movement, right? We have 10 minutes. We can complete movements. So moments 1.3.3. These all you know, just it's brushing kind of thing together. So moments. So nth order moments of a random variable x could be defined as e of x to the power n will be equals to minus infinity to plus infinity x to the power n f of x small x dx, right? Now you see why we call this is nth order moment. Why we called mean as a first order moment? Because n is 1. So as for mean n equals to 1, so it is first order moment. And what is the value of zeroth order moment? Zeroth order moment e of x to the power 0. What it will be? Tell me quickly.
1.
1. So zeroth order moment is always 1. That is why it has no importance or physical significance. If it changes, then only it has carries physical significance. Na? Okay, so for discrete PDF, let me say it. For discrete PDF, e of x to the power n will be equals to summation over k xk to the power n pr of x xk. Okay, so this is the nth order moment. So zeroth order moment is 1, so we don't have much importance, and we have importance on higher order moments definitely, so that we'll gradually discuss. Okay, so so now discussion we ends here. A lot of discussion we made without any interval or any break. In class generally we give 5 minutes break, and it is class, it is slow. In online you can pace it up. So now all of you tell me, so is it fine till now whatever I covered? So what you need to do, you need to solve various problems. Okay, so these are the all full theory, nothing I am excluding. So you have to solve various problems from any book. Any book you solve workout problems, you solve exercise problems. Okay, so that will be helpful for you. Particularly this probability problem, no need to solve because we are not going to calculate what will be the probability of this, that is tedious. Also you need to know this permutation combination, but you try to solve this random variable, sample space, then probability density function, and put more emphasis on the conditional variables or the conditional distribution. Okay, so those things you put more importance, and gradually moment calculation, all those things. So you solve examples, that is what is required. Okay, so now we save it. So let's stop here, stop recording. I say that to us probability mass function is less familiar than the discrete PDF, although both are same. So now, so what may be the expectation? So expectation of x in such cases will be summation of xk multiplied by probability of x at xk sum. That means x1 into the probability plus x2 into the probability plus x3 into the probability. Like this you go, you sum it. That means it is a weighted sum. So it is a kind of weighted sum. So you will get the expectation. So this is the weighted. So this for random variable you could write like this. For continuous variable you could write like this. So both are same. Okay. So now tell me if you understand it. Is it fine? How the expectation is coming? How we can write the discrete PDF? How we can write the expectation of discrete PDF, right? So here one thing I must say, that when I say that expectation of this equals to summation of this, I must say that it is a simple weighted average, but the expectation exists if the sum converges. If the sum converges, that means this is a series, right? So if the sum converges, then the expectation exists, otherwise it does not exist. Okay.